Bismillahirrahmanirrahim. Assalamu alaikum. So today, inshallah, we have this new chapter that we'll deal with, which is a very important chapter. Okay, and the title of the chapter is called an image transform. Here, by image transforms, I mean what type of transforms actually. I think in the courses of the signals and systems, you have seen that if I have a signal in the time domain, right, I can analyze it, okay, by transforming this same signal into its equivalent signal in the frequency domain, okay, so that I can see what type of frequency components do I have. Do I have, for example, dominantly I have high frequency components or low frequency components and so on. Same thing here when we talk about the image transform. But here for the image transform, here we need to make a transformation between the spatial domain, the space, in which we have the rows and columns of the image, into its frequency domain. By the frequency here, I mean this color is to be repeated in which type of frequency. Maybe, for example, I have the image has, all of the image has the same color. So in this case, I don't have any changes. So this means that the frequency of change is equal to 0. Okay? And this will be the dominant frequency. Or maybe, for example, the image consists of is full of details. So in this case, this means that the colors will be changing with a higher frequency. So in this case, I will have high frequency components. Okay? So for this transforms, actually, I can use them in order to do basically two things. First of all, if I want to filter the image, for example, the image consists or contains noise, so I want to remove this noise, I want to reduce the noise. Okay? Or the other way in which we can use this transform is to compress the image itself. So here, if we talk about the image transforms, we find that it has two main purposes. Also, we have other purposes as well. But the two main purposes are to filter the image by removing noise or to compress the image. Okay? Before continuing into this topic, first of all, I want you to know how to install the camera or make your camera work with MATLAB. Okay? How many of you have succeeded to make the camera work with MATLAB? Actually, here the camera, the built-in camera that you have in the laptop, you want to see how can we make it work inside MATLAB. What type of commands we need to give to the MATLAB so that the camera will work. To take, for example, to capture, let's say, frames. How can we make the MATLAB identify the camera? Okay. So how many of you actually have succeeded in making the camera to work in MATLAB? You didn't try it? Okay. So I will give you a small hint here. With respect to the old versions of MATLAB, actually, the MATLAB was installed together with the camera drivers. Okay? For the time being, this is not the case now. The MATLAB is to be installed first. Then after that, according on demand, you can make an add-on. Okay? You can select an add-on that corresponds to the camera hardware and you can install it. Okay? So from where can I get this information actually? If you look at the blackboard, if you go to the blackboard of the course, it's here, I think, this one. In the contents, you will find that here how to install the camera in MATLAB. Actually, here you will have a link. Okay, just copy it. Okay, this is in the page of your. So here, if you go to the page of the course, in the course contents, okay, you'll find here at the bottom how to install the camera in MATLAB. Okay, here you will have a link, a small link. Okay, just copy it, Control C, and we can go to the, let's open a new tab, Control V, and this actually is a help page that's provided by the MathWorks. So here in this page, it describes what we need to do actually, okay? So first of all, here he's saying to install a support package for the camera that you want to install. On the MATLAB Home tab, use the environment section and click on add-ons, get hardware support packages. So So this means that I need to go to the environment of the MATLAB, okay? We need to go to the Home tab, and from it we'll use the environment section. So let's go to the MATLAB here, this one, okay? This is the Home tab, and we'll go to the environment section and add-ons. And below the add-ons here, we'll select Get Hardware Support Packages, okay? And I will select an action here which is installed from internet. Okay, like this, it will connect through the internet and it will install the corresponding add-on that we need. So I will press next, and here you will find a GIGE Vision hardware. This is the hardware that I have installed, in fact. Okay, this is the hardware that I installed. So actually, when you go here, GIGE Vision hardware, just select it, and you need to check this button. Then after that, you need to press on the next. And like this, actually, the driver will be installed. Okay? Right? If after the driver is installed, actually, you can, from the MATLAB itself, you can use the camera by using this video input command or video input function. Okay? You can put it like this. X equals video input. And between single quotes, you need to specify here. When video, this means that it will select the default video device that is installed in your machine. Okay? And here you need the first, let's say device that has this name. And then after that, when you issue this command, let's try it, X equals video input, it will create an object of type video input. Okay? Once this object is created, now you are ready to use this object in order to open a preview to see what the camera actually is capturing, or to get a snapshot. Capture, for example, a certain frame. And in this case, once it is captured, it will be stored like a normal image, and you can do whatever processing you want to do. Okay? If you want, for example, to do this processing in a continuous manner, so in this case, this capturing operation, it needs to be enclosed inside a loop. So each time you enter inside this loop, capture the image, do the processing. Then after that, go back to the start, capture another image and do the processing again, and so on. Okay? So here we have this image. Also, we have other functions that can give us some information about the object that we have created here. So here we have something that's called image acquisition hardware information, okay, which is the IMAQHW info, image acquisition hardware information, and give it the object that you have just created, Control C. It will give you some information about whether you have an installed driver or not. So here actually we have the adapter name here is called WinVideo. It's an integrated camera. It's the maximum height and maximum width of the generated, let's say, images. We have here the native data type, which is unsigned integer 8, and so on. Okay? Type. So this is the information. Type. If I want to see the preview, what this camera is seeing now. So actually here I have preview of X. I need to pass it again, the video object that I have created. Okay? So here Control C. We'll pass it here as a command, Control V. So this is the what is the camera is capturing for the time being, right? Type. Actually, here what we see is just a preview of what is the camera is seeing. For example, if I want to capture, or let's say to take a snapshot of an image, I will call the function that is called getSnapshot. Together I will pass to it what? The video object again. Okay? Once I say getSnapshot of X, the return value, it will be the matrix that corresponds to this image. Okay? So let's try it here. For example, I will make something like this. Control C, Control V. So now as you can see here, the Y is the dimension that you have just seen. Here it has 480 rows, 640 columns, and it has 3 layers. So this is a color image. Okay? And it's stored here in the matrix Y. If I want to see it, I will use the normal image show function. Okay, so here we'll say that figure show of the matrix that is generated here. So it will be something like this. So this is the image that was captured. Okay? Once you have this image, you can make any processing you want to do. Okay? So this part of the get snapshot, together with the processing that comes after it, this can be enclosed within a loop. So in this case, you are continuously getting the new snapshots from this camera and you are doing the processing and so on. Okay? If you need to do such thing. طبعا, of course, here, maybe I didn't mention this function which is called IMWrite. We have seen the IMRead, to read from a file. Now, for example, I have the image is in a matrix and I want to store it as a file on the hard disk. Okay? So in this case, we'll use the IMWrite function. The IMWrite function here, I will pass with this arguments. Here in general, we have 3 arguments. The first one here is the matrix that corresponds to the image. The second argument here between single quotes, this is the name of the file that will be generated. And the last item here, this is the type of compression that I want to do, whether, for example, it is JPEG, GIF, PNG, whatever. Okay? So, for example, we can say something like this: IMWrite Y. Let's say, مثلا, my image dot JPEG. Yes. 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 Okay. Right. This image, actually, once I have done this IMWrite, this image has been created now. So where it will be created and where it will be saved, actually it will be saved in the current working directory or in the current folder. So let's see here. First of all, I need to minimize this one. Just to see what do we have here. It was called out my image. I think my image should be here. It's up there? I can see it. Yes, this one. So here we have my image, which is the image that we are talking about. So now, for example, once the image is stored, I can deal with it in the normal way that we are used to. For example, I can say that I is equal to IMRead of my image dot JPEG, like this. Then after that, I can display it in the normal way that we are used to, okay, of I. So this is the image that we have just captured and saved. Okay? So now we have seen how can we deal with the video. First of all, I need to create the video object by using this video input command. Right? Give it these parameters. Then after that, I can, if I want to see a preview, a continuous preview, as you can see here, the preview is still running, right? Okay? If I want to get a snapshot, I will call the get snapshot function. Okay? If I want, for example, to do a processing, once I get the snapshot, I can do the processing. Okay? If I want to save it, I will just call what? The IMWrite. Okay? So I've seen some functions that can be useful for you when you start working on the project, when I give it to you, inshallah. Okay? If I want, for example, now I have finished with this video object, I can now delete the object itself. So I will call delete of X. Okay. So now, for example, when I say delete X, actually the image or the, let's say the video object now is deleted. So nothing is captured anymore. Okay? X does not exist anymore. Okay? Right? So these are the small hints that we want to talk about with respect to the camera that is connected to your laptop, or for example the webcam that is connected to your laptop, and so on. Right. Let's go back to our chapter here. Yes? No? Yes. It will delete the object. Okay? So because actually when you create the object, it takes space from the memory. Okay, so if you don't need this camera anymore, you need to delete the object that corresponds to this camera capturing device. No? No, delete the object. The object was called X. Okay, the object that was used with the video input command. Okay, if you remember, it was the matrix in which I have read the image. Right? Clear? So here, let's go back to our image transform here. For the image transform, as you have said before, here I need this transform in order to transform my image from the spatial domain to the frequency domain. Why do I need to do such kind of transformation? Merely to filter the image, okay, so that I can have my image. Instead of having it in the spatial domain, I will have it in the frequency domain. So if I want to filter the noise that exists in the image, the noise merely they have the high frequency components. Okay, so in this case I can suppress the high frequency components. Then after that I can make an inverse transform from the frequency domain to the spatial domain again. So like this, I will find that the effect of the noise actually to be reduced. Right? Another thing is that I can use it for the compression. We will see later how can we use this image transformed for compression. Okay? Because when we suppress the high frequency components, I will find that in my matrix, I have lots of entries inside it that are having zero values. Okay? All of these zero values actually can be ignored. Right? So in this case, I can compress the size of the image. So the image actually it will be compressed in the frequency domain. Okay? So here we say that image transforms, they decompose an image into a data space where characteristics that are otherwise not visible in the original image. Okay? Like for example, if I have the image in the spatial domain, I have the image, the normal image that I am seeing. With the normal eye, I cannot say what frequency components exist and what frequency components does not exist. Okay, so I need to transform it to this frequency domain. So actually here it decomposes that image into a data space where characteristics that are otherwise not visible in the original spatial domain image. Okay? Right. Here we say that usually transformation is bidirectional. For example, if I can transform from the spatial to the frequency, okay, I can transform again from the frequency to the spatial. Right? And the original image can be restored using the inverse transformation. Right. Here, one of the famous types of the image transformations is what? It's the Fourier transform. Okay? So how many of you actually knows about the Fourier transform or heard about the Fourier transform before? Signal systems, huh? Okay. So here we say that Fourier transform is very well established technique in mathematics, and it is useful in describing a signal in terms of its frequency, instead of in terms of the value of the pixels with respect to space. Okay? Now I will say, for example, for this frequency component, for the high frequency component, what is the level? What is the amplitude? For the low frequency component, what is the amplitude? For the high frequency, and so on. Okay? So actually here, what was the main idea of the Fourier transform? Do you remember? Salam. Any ideas? You don't remember what was the... How do we make this kind of Fourier transform from the, let's say, from the time domain, as you are used to? Yes? Integral, yes? Okay. And what is, yes, we have used the integration, sure. The integration of what?
Of the convolution.
Of the convolution, yes. Convolution of what with what?
actual function by another function.
Yes, the actual function, or the, let's say, the function in the time domain, multiplied by a certain basis function. Okay? And this basis function, it is in the form of sine and cosine with different frequencies. Okay? Right? So the idea is that I have my signal and I will multiply it with sine and cosine functions that are having different frequencies, and I will get the average of the result of this multiplication. Right? Okay? So the idea, for example, here Fourier, the basic idea, the simple idea here said that any signal in the time domain or even in the spatial domain can be represented in the frequency domain as the summation of sinusoidal signals, okay, with different amplitudes. And to be more accurate, as a summation of sine and cosine signals with different amplitudes. Clear? Okay? So here we say that in an image, the frequency components here are related to both height and width of the image. Okay? You have the frequency components. We'll see here what is the meaning of the frequency components. If we compare the case of the Fourier transform that you have studied in the signals and system with the frequency or the Fourier transform here that we will study here in our case of the image, we have some differences. Okay? In the signals and systems, we have considered that my initial or original space was the time domain, right? Okay? And it was continuous. Here in this case, our original space is a spatial domain and it is discrete. I have pixels. It is not continuous. Right? So that's why here, instead of using the Fourier transform, I will use something else which is called a discrete Fourier transform. Okay? Right? So here, for this discrete Fourier transform, the height and width of the image will play a very important role in specifying the frequency components, as we'll see, inshallah. So here we say that another thing that is related to Fourier transform in general, whether we are talking about spatial domain or time domain, sudden changes in the grayscale, in the original signal, okay? One pixel that is white and the pixel that comes directly beside it is black. Okay? This means what? This means that I have a high frequency component there. Okay? But on the other hand, if I have, for example, a constant or consistent gradient or constant levels, okay, these are related to what? The low frequency components. Okay? I don't have much change between the pixel and the pixel that comes directly after. Okay? So we say that computationally a variant of the discrete Fourier transform is utilized, and it is called fast Fourier transform. Here, for the discrete Fourier transform, we have even better type of Fourier transform, which is called fast Fourier transform. And this is the transform that we will use. Yeah, and this is the Fourier transform actually that is implemented in MATLAB. Okay? It has better performance than the original discrete Fourier transform that you are used to. So this is for the Fourier transform. Another type of transform. Take care of something. All of the transforms that we'll talk about today, actually we'll talk about them in details afterwards. Okay? Another type of transform is called the wavelet transform. Did you hear about the wavelet transform? Okay. Who can tell me an idea about what we mean by wavelet transform? Yes. 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 And here the basis function, do we need the sine and cosine?
No, we have a lot of wavelets.
Exactly. Here we have something which is called a mother wavelet. Mother wavelet, the simplest form of a mother wavelet, it can be in the form of, let's say, square wave. Okay? And we have some other more, let's say, sophisticated mother wavelets. Okay? We will not enter into the details of the wavelet transform. In this course, actually, we will use these transforms to reach our goal. Okay? But of course, to do such thing, we need first of all to understand what do we mean by such kind of transforms. So in this case, we will not use the sines and cosines, but actually we use something that's called what? A mother wavelet. So we say that it does a similar thing as Fourier transform, but changes the view window from large window to smaller one, that are called scale. So actually, with each level of transform, our image actually will be scaled down. Okay? And it will generate 4 different, let's say, components. I will have a scaled down original value of the image. I will have the frequency, let's say, components in the horizontal direction, the frequency components in the vertical direction, and the frequency components in the diagonal. Okay? And we can do such type of transform in a continuous way. Okay? As we'll see later. So here we say that this is something that's called what? Scaling decomposition. Scaling decomposition. I'm scaling down the image. Okay? From let's say n by n, it will be n over 2 to n over 2. Okay? And in this case, I can isolate the frequency components in the different directions. Horizontal, vertical, and diagonal. As we'll see later. Okay? So we say that unlike simple sine cosine basis functions that are used for the Fourier transform, here for the wavelet transform you use some other type of basis function which is called what? The mother wavelet, as you have said before. Okay? So here we have a number of these mother wavelets. Actually we have lots of mother wavelets. Actually we can compare them with respect to the amount of information that it can give us. Okay? So the wavelet transforms are primarily used for noise removal as well and compression applications. Okay? So all of the type of transforms in general are used for the noise removal, which is the filtering of the image, as well as compression. Okay? Right. Another type of transform, which is the third type of transform, and the last one is called Hu transform. Okay? Hu transform actually is a classical technique that can be used, for example, to identify shapes. I can use this Hu transform in order to identify in a certain image if I have straight lines, or if I have circles, and so on, as we'll see later, inshallah. So here the application that we'll do with this Hu transform, for example, if I want to identify if I have a straight line in my image or not. Okay? And how can I detect this straight line, and where can I find this straight line in the image? Okay? So as you can see from here, we have, this is another, let's say, application of using the transform. In addition to the noise removal and the compression, I can use it to identify shapes. Okay? All of these actually they are depending mainly on some mathematical background, as we'll see. Fine. Let's go back to the Fourier transform and try to get familiar with the Fourier transform and try to understand. For example, if I have a signal and I found the Fourier transform for this signal, how can I read this transform? Okay? Right. So here we say that the Fourier transform is an important image processing tool. It's an important one that is used to decompose an image into its sine and cosine components. Okay? So it's a summation of sines and cosine. The output of the transformation represents the image in the Fourier, we call it Fourier domain or frequency domain. Okay? And the input image, the original image actually is in the spatial domain. Spatial comes from the word space. Okay? I have rows and I have columns instead of time, in the normal way that we have used before. And in the Fourier domain image, each point, the Fourier domain, each point represents a particular frequency. So for this particular frequency, what is the amplitude of this image? Okay? So for this frequency, if I have a considerable amplitude, well, this means that this image contains this frequency component. Okay? If the amplitude is small, well, this means that this image does not contain this frequency component. The Fourier transform here is used in a wide range of applications, such as, for example, analysis, image filtering, of course, image reconstruction, and image compression. These are the uses in which we can use this kind of transform type. This is the photo of the scientist. It's called Fourier. It's called Jean-Baptiste Joseph Fourier. And he was born in this state on 1st of March 1768 in Auxerre-Bourgogne, France, and he died on 16th of May 1830 in Paris, France. Okay? And he was a great mathematical scientist, in fact. So here, we say that this Fourier transform is a representation of an image in 2D frequency domain. 2D, this means that I have two dimensions here. Okay? So here in the normal frequency, in the normal, let's say, Fourier transform that you are used to, here I have a function f of t, against time. So actually here I am dealing with one dimension, which is time. Okay? and I have a corresponding, let's say, frequency domain transformation of something like this. Right? Okay? But here, when we talk about the image in the spatial domain is already a two-dimensional image. Okay? I have the horizontal dimension, I have the vertical dimension. The frequency, or let's say the Fourier transform of this image, it will have two dimensions as well. Okay? Which will give me the frequency, let's say, variations in the horizontal direction and the frequency variations in the vertical direction. Okay? So here I have a 2D frequency domain. Here, of course, representation using exponentials. Here, actually, he is referring to the, if you remember, the basis function. And here we are using this exponential a to the power j something, okay, a to the power j cube. This is the summation of cosine cube plus j sine cube, right? And this actually, later we'll see the basis function. The basis function is written in this way, e to the power j something. Okay? So here we say that Fourier transform represents samples of the image into two-dimensional series of sines and cosines. And given an image A, here small a, this is the original image, and its Fourier transform capital A, uppercase A, then the forward transform goes from the spatial domain, okay, to the frequency domain. Okay? So here we say that capital A is the Fourier transform of small a. And as well we have the inverse Fourier transform. We can go from the capital A to the small a by applying the inverse Fourier transform, okay, which is represented by f to the power minus 1. Okay? Here Fourier, this is the basic principle that Fourier has put his work on. We say that an arbitrary function, any function, okay, continues or with discontinuities, like for example the discrete function that we have, defined in a finite interval by an arbitrary capricious graph. Capricious graph, this means that it can be represented in a graph, okay, in general, can always be expressed as a sum of sinusoids. Okay? Here actually is describing exactly the image. Okay? So here the image is a discrete that has a finite, let's say, extension. It has a width and length, so it can be described as well in the form of summation of sinusoids. Here, for example, we can say that translation, here is talking about translation. For example, if we take the square wave, we can say that the square wave is the summation of several sinusoids. The fundamental, let's say, component, the third harmonic, the fifth harmonic, the seventh harmonic. So actually it is the summation of the odd harmonics. Okay? With an amplitude that is directly proportional to 1 over n, where n here is the number of the harmonic. Okay? Can we prove this? Yes, we can prove it practically now, using the MATLAB. So here we say that translation would superpose sines and cosines of different frequencies to represent other functions. Let's look at something like this here. If we go back to MATLAB, we will see a very small function. I think I have written it here somewhere. It's called, yes, this one, square. Okay. During this function, I will postulate the number of harmonics that I want to add. So for example, here if I say 7, so it will add the first, third, fifth, and seventh harmonic. And you will see what will be the result. Okay? And here we have the range of x, and this is the y in which we'll have our function. And the function will be something like this. This is the addition of several harmonics, okay, having amplitudes that is inversely proportional to the number of the harmonic. This is exactly the, we can say that this is the analysis of the square wave. Okay, it is the summation of the odd harmonics. Okay, so here we can say that for the square wave, it is something like this. Let's say مثلا f of x. It is sine x plus 1 over 3 sine 3x plus 1 over 5 sine 5x plus 1 over 7 sine 7x, and so on. Right? And as well, each time we are adding new harmonics, this will make our shape of the square wave become nearer to the value of the square. So actually here when we say something like this here, square, for example, I want just the first harmonic. What do I expect to have here? It's just a simple sign, okay? Which is this one, okay? Type when I say, for example, square 3. So here I will have sine x plus 1 over 3 sine 3x. So you have something like this, okay? So now we are approaching a little bit to the shape of the square wave, right? Type if we, for example, take a higher harmonic, let's say, مثلا here, instead of 3, I will take 9. So in this case, I will have the first, third, fifth, 7th, and 9th. So it will be something like this. So we're approaching more and more to the shape of the square wave, okay? So as much harmonics you will add here, let's say مثلا 21, I will find that the shape will go nearer to the square wave. مثلا let's try something crazy here, 1001, okay? So 1001 here, as you can see, it will give me exactly what? Square wave, right? Okay? Here, this type of analysis is useful for us, so that, for example, after a certain level of harmonics, I can make filtering to my signal, okay? And I can consider that, for example, here for the 7th harmonic, it is fine with me. This is acceptable for me, right? So in this case, I can make some sort of low-pass filter, okay, in order to suppress all of the frequencies above, let's say, the 7th harmonic. Like this, I will suppress most of the noises that can be added to the signal, because the noises actually are having high frequency in this range. See what I mean? Is it clear? Okay. It is saying that this translation, we could superpose sines and cosines of different frequencies and different amplitudes as well to represent other functions. Right. Here the Fourier transform that we are used to, it is a double integration of the original signal multiplied by e to the power minus j ux dy dx dy, where here x and y, are the dimensions of the original space, okay? And uv, these are the dimensions of the frequency space, frequency domain. So here, مثلا x and y, this is the spatial domain, u and v, this is the frequency domain. Okay? In general, if we look at the Fourier transform, the discrete Fourier transform, and the fast Fourier transform, how it will be applied on our image. If I have an image of this dimension, let's say this is in the spatial domain. It has this dimension. Let's say, مثلا, here I have, this is the number of columns, and this is the number of rows. Okay? And I will convert it by the Fourier transform, okay, in the frequency domain. What will be the dimension of this image in the frequency domain? Actually, it will be the same. It will be the same. Okay? But here, instead of the special, here, if I say, for example, in row number I, column number j, this pixel here, it represents the intensity of the pixel. Okay? Here, for example, if I have row number u, column number v, this point here, it will give me the amplitude of this frequency component. Okay? The frequency value in the row direction u with the frequency value in the column direction v. It has this amplitude. Okay? So here, we say that as we are only concerned with digital images, we will restrict this discussion to the discrete Fourier transform. Okay? Discrete Fourier transform. This is the transform that we use. So here we say that the discrete Fourier transform, if we compare it to the original one, is the sampled version of this Fourier transform. And therefore does not contain all frequencies. Of course, here I don't need all of the frequencies. The frequencies that will be used here actually they are discrete frequencies. But only a set of samples which is large enough to fully describe the spatial domain image. Here we say that the number of frequencies corresponds to the number of pixels in the spatial domain, as we have said before. Okay? So here the number of the frequencies that I have, it will be equal to the number of the pixels in the original image. Okay? Except in some, let's say, as we'll see in some special cases. Let's say the image in the spatial and the Fourier domain are of the same size. This is very important thing here. The images are having the same size. Right. So here for the square image of size n by n, for example, the two-dimensional discrete Fourier transform, it will be something like this. It is f of kl, where kl here represents the, let's say, the axis in the frequency domain. Okay, is 1 over n squared, which is the number of pixels, double summation from I equals 0 to n minus 1 and j equals 0 to n minus 1 of the original image here, which is f of ij, multiplied by the basis function here, which is e to the power minus j 2 pi, this expression. Okay? Right? So here we say that f of ij is the image in the spatial domain, and the exponential term is the basis function corresponding to each point fkn. So how can I read this equation here? For example, for a certain point, let's say in the frequency domain, let's assume, for example, that this is k and this is l. Okay? So here I am interested in getting the frequency component for the horizontal direction. Here I have k, and for the vertical direction here I have l. Right? How can I get this frequency? By multiplying the whole image, as you can see. Okay, by this kernel function with this frequency, which is k and l. Okay, so here k and l, they appear as a frequency in the basis function. And as we have seen before, e to the power j something, e to the power j x, for example, this is corresponding to cosine x plus j sine x. Okay, so I'm multiplying my image by this cosine and sine with these specific frequencies. Okay, and I'm interested in getting what will be the frequency component for this value of frequencies. Okay, what will be the amplitude of the image. Okay, so if this k and l, they are of high values, and I found here, for example, the result of evaluating this expression, I have a high value, where this means that this frequency contains high frequency components. If I have low values here, this means that it contains low frequency, and the high frequency components are not dominant here in this case. Okay? So here we say that Fij is the image in the spatial domain, and the exponential term here, which is e to the power minus j2 pi, so and so on, is the basis function corresponding to each point at k and l. Okay? In some cases we call them kl, other cases we call them uv, so they mean the same thing. Okay? So all of the time here I'm referring to the frequency domain. Okay? Fine. So here the equation can be interpreted as the value of each point, f of kl, is obtained by multiplying the spatial image with the corresponding base function and summing the results. So as you can see from here, that this exponential term, it will be multiplied by all of the, let's say, pixels that I have in this image. And I will make a summation of the result of this multiplication. Right? Okay? Here is saying that the basis functions are sine and cosine waves with increasing frequencies. So when we say f of 0, 0, it represents the DC component of the image, which corresponds to the average value. Okay? Here when the frequency is equal to 0, this means that I'm interested in the average value, the value that does not change. Okay? The average value of the whole image. And f of n, it represents the highest frequency. Here actually it should be n minus 1, n minus 1. I will see later why it is divided by 2. Okay? But for the time being here, as n increases, this means that I am interested in the highest frequency components. Okay? Here also, since we have this kind, we have said that this kind of transformation is bidirectional. So as we have the transformation from the spatial to the frequency, I have as well from the frequency to the spatial by using this inverse Fourier transform. Okay? It has almost the same expression, except here instead of e to the power minus j, here I have e to the power plus j. Okay? Right? And of course here I am transferring the image in the frequency domain to its corresponding image in the spatial domain. Okay? Do you have any questions so far about what we have said? Shortly we will see some examples using MATLAB, just to get used to the functions, how the expression. But let's look here at the resulting values that I will have here from this expression of the transformation. F of KL, actually this value is a complex value. This means that it has a real and an imaginary part. Okay? It has a real and imaginary part. So here if we look at this slide, it's saying that the Fourier transform is in general a complex function. This means that the resulting values are complex functions, okay, of the real frequency values. As such, transform can be written in terms of its magnitude and phase. So actually here we can say that for any, let's say, point in the frequency domain, it can be represented as a magnitude together with a phase, right? Since it's a real plus imaginary plus j imaginary part, this means it can be represented in the form of magnitude and phase, right? So, for example, if I have let's say a function like this, function of uv, I have u plus iv, right? This is a complex function, right? What is the magnitude here? This same function can be represented like this. A magnitude, which is a magnitude of u and v, together with the phase of this function. What is the magnitude here in this case?
U.
The square root of u squared plus v squared. Okay? And the phase here will be 10 minus 1, the imaginary part divided by the real part. Right? Okay. Right. Here we say that if a 2D signal is real, here is referring to the spatial domain. In the spatial domain, the values of the image, the intensity, they are real or complex? They are real, okay? They are not complex. So all of the values, actually, they are having real values, right? So then the Fourier transform has certain symmetries. So actually here I will have a symmetry. So here I will find that, if I'm talking about the Fourier transform of the image, I will call it capital A of uv. I will find that the magnitude of A uv, it will be equal to the magnitude of A minus u minus v. Okay? So here actually it is symmetrical about the 0, 0. Right? As a magnitude. The frequencies as well, here I will find that here uv is equal to phi minus u minus v. Actually this one, yes, maybe here we need, this is not 100% correct. Okay, maybe here we have a sign. We have here a phase shift of negative actually. So here phi uv is equal to negative phi of minus u minus v. Okay, fine. And this is something for your own knowledge, okay? And I will not test you on this, but I want you to understand, okay, what is the meaning of this transform and how it is created. So we say that if a 2D signal is real and even, then the Fourier transform is real and even. Here by even, this means that the value of the negative part, okay, is equal to the value of the positive part. If we apply, for example, the values of the pixels. But here, the main idea is that that is important here is that the image, it has real values. It has real values. Right. Also something else which is about the properties, we say that the Fourier and the inverse Fourier, both of them are linear. So if I want to, let's say, get the Fourier of transform of this expression, where A and B here are our variables, W1 and W2, these are weights, these are constant coefficients. This is exactly equal to the Fourier of W1A plus the Fourier of W2B. It's a linear, okay? And W1 here can be taken as a common factor, okay? It's equal to W1 Fourier of A plus W2 multiplied by Fourier of B, okay? So here, this is a linear operation. Type. Now let's go to the MATLAB to see some examples. We'll clear it like this. Let's assume that I have this expression. X is equal to zeros. Here I have number of rows, Helena 1 and 1000 columns. So here actually I have created just a one-dimensional signal that's called X, okay? And it consists of zeros, okay? 1000 zeros actually. And I will apply to it the discrete Fourier transform. Okay, in this case, the original signal is discrete, as you can see. I will apply to the discrete Fourier transform. And the Fourier transform that is applied here actually is called fast Fourier transform. Here in this case, I will make something like this. Let's say X is equal to 100 X. So here if I look at the values of X, it is 0 of course. X plus 100X. X will be 100. So this means that all of the values are equal to 100. If I get the Fourier transform for this expression, what do you expect to have? I will have a value for the Fourier expression that corresponds to the zero frequency. Okay? And all of the other frequencies that are having non-zero values, actually their component will be equal to zeros. Because actually I don't have any changes at all. All of them are constant. So now let's prove it here. Assume that I will say that the resulting, let's say the Fourier transform signal, I will call it capital X, FFT of X. This is the function that can be used in order to get the fast Fourier transform for a single dimension signal. Okay? Now let's see here how it works. Okay. Now I want to see the values of X, right? So we can make something like this. If I want to get where can I find values of X that are having a certain condition, let's say that are having values greater than 0, I can use the find function that is used in MATLAB, okay? Do you know the find function here? So I can say find X greater than 0. When I make something like this, it will return what? X here, this is the matrix in which I want to find, in which I want to search, okay? Find X greater than 0. It will return what here in this case? Yes, it will return here the value of the indices for which X here is greater, for which the value of the elements here are greater than 0. So here I will find something like this. So here, as you can see, I have only just one element that have a value greater than 0, which is the first element. The first element here corresponds to the 0 frequency. Okay? The first element here corresponds to the 0 frequency. So here, if I want to see what is the value of this element, just apply X. It will be something like this. 100,000, something like this. Okay? 100,000. Okay? Right? If this value I will divide it by the number of pixels that I have in X. Okay? Here I can normalize this value. How can I get the number of elements that exist in a certain matrix? Yes? How can I get the number of elements that exist in a certain matrix? Other than the size. Yes, the size, it will give me the dimension. I have how many rows, how many columns, etc. Length, yes, length can be applied on vectors, yes. And also we have another function that can be applied on vectors and matrices, which is called num L, or number of elements. And here between brackets I can give it what? The value of x here. Right? So here it will give me what? 100. 100 here is what? This is the average value. Okay? So here in this case actually I have just one component in the resulting frequency, as you can see, which corresponds to what? Which corresponds to the average. Right? Right. Another question? Yes? Yes, about the average. Actually, here, if I want to get the actual values of the frequency components, okay, I want to get the actual values of the frequency components. Actually, when I say f, here it is not f. When I say x of 1, which is the first element here in the result of the Fourier transform, this will give me the amplitude of the zero frequency. Zero frequency means what? Means I am talking about average. Okay, what is the average? What is the value that does not change? Understand? Right? Right. Here, when we talked about, let's say, the value alone, when I say مثلا x of 1, it was found that is equal to 100,000. Okay? This value is not the correct value, it's not the normalized value. To get the normalized value of the Fourier transform component, I need to divide it by the number of elements in this x. Okay? If I divide it by the number of elements, actually it will give me what? 100, which is the correct value that I'm looking for. Clear? Okay? Fine. Now let's play with this signal a little bit. Assume that I have something like this. I have here 1, 2, 3. These are the indices of the elements that I have, right? It starts from 1, 2, 3, 4, etc. Up to what? Up to 1,000. Okay? During this period, what is the number of times that this this signal, for example, can change? Can change in a periodic way. Let's say, here at 1 I will have 0, at 2 I will have maximum value. Then here 0, then a maximum value. Then 0, then a maximum value. Something like this. Okay? During this interval here, this chain, what is the maximum number of times that it can be repeated? It is divided by 2, exactly. So this means that the maximum number of times that this signal can be repeated within this range is equal to how much? 500 times. 500 times. So I will do something like this here in this signal. In this signal, initially all of the values are equal to 100. What I will do actually is that for the odd indices, I will add, let's say for the even indices, assume that I will add a certain offset. So I will add at index 2, 4, 6, up to 1000. Okay? So like this, it will have this kind of chain. So how can we do this? We need to manipulate our signal. I will say that starting from 2, with a step of 2, up to 1000. This will be equal to the original value. And add to it what, say, مثلا 100 or something. Okay? So here in this case, what we have done here, we are selecting the indices of the elements at 2, 4, 6, 8, etc. Okay? And I will add to them a certain offset of 100. So I will have a signal like this one. Right? Let's see here. And let's make sure that things are going as we are expecting. So here we will plot it. Let's plot مثلا a part let's say مثلا range from 1 to 40 of this x. Okay, so as you can see from here, the odd values are having values of 100, okay, and the even values are having values of 200. Okay, and now I want to get the fast Fourier transform of this signal. Okay, what do I expect to have here? I have two values. Okay, the first value is the average value, which is at 0 frequency, and the second value, which will be at what value of frequency? This signal actually, what is the frequency of changing this signal? This means that for the whole range from 1 to 1000, this form of signal, it will be repeated how many times? 500. So this means that at 500 as well, at the frequency 500, I expect to have another non-zero value. And all of the other values of the frequencies, I expect to have what? Zeros. Okay? Let's prove it. Again, here we need to make something like this. We'll convert it. Okay? Then find. Let me see here. FFT x not equal to 0. Actually, here I have two values in which the value is not equal to 0. At 1, which correspond to 0 frequency, at 501, which corresponding to frequency 500. Why do I have frequency 500 appears in 501? Because of the indices of the MATLAB. The indices of the MATLAB starts from 1, not from 0. Okay? So here, let's look here at these values here. خلينا نشوف. Here I have x of index 1 and index 500. So here, in index 1, I have 150000, and in index 501, I have this value. So this means that I have only just frequency components at the 0 frequency and at the 500 frequency. Clear? Okay? And as we have seen before, the Fourier transform of this signal, since the original matrix has the size of 1000 elements, its Fourier transform will have 1000 elements as well. Okay? Right? حاجة بس كده صغيرة. Let's make something. أيوة 4. I will change this values, okay, by adding 100. What did I do here actually?
We will have only 250 repeated shells.
So this means that I'm adding a signal that will be repeated 250 times. Okay? خلينا نجربها كده ونشوف. Let's apply it here and get its corresponding, let's say, frequency. خلينا نشوف برضو non-zero values. Yes. So actually here I have a component at 1, a component at 251, this means 250, component at 501, which means 500, and here I have a component of 751. Actually here when we look at the Fourier transform that is generated here, after the 501, I will find that all of the values that exist from 502 up to 1000 is a mirror image for the values that exist from 2 to 500. Okay? What is the meaning of this? This means that if I look at the value in general at 500, it will be equal to the value at 502. And the value just before, which is 499, it will be equal to the value at 503, and so on. So this means that the Fourier components that are generated here, I will find that they will be repeated. Actually, it is equal in magnitude. Okay? But if it is a complex value, it will be the complex conjugate of the value. If this value has a positive imaginary part, this value will have a negative imaginary part, and vice versa. But they are having the same magnitude. Clear? As we'll see later. So now if we look at the, let's say, these values. Okay. How can I read these values? We say that all of the values will be multiplied by 1 times 10 to the power 5. Okay? The first value here is 1.75 plus 0 r. Okay? This corresponds to the index 1. The second one here corresponds to 151. This is 501. And this is 751. Okay? If we look at this 501, this corresponds to the highest frequency, which is repeated 500 times. Okay? Both of these two values, they correspond to the 250 times. The expression that is repeated 250 times. What is the relationship between this and this? They are equal in magnitude, but they are complex conjugate to each other. Okay? If I get the magnitude of this expression, it will be exactly equal to this magnitude, but this one is complex conjugate to this one. Okay? Right? Inshallah, next lecture, we will try to do more examples, then after that we will apply this on the two-dimensional images that we have. And we'll try to read the Fourier transform of the images that we have and compare them. Okay? Clear? So we'll stop here and we'll continue inshallah next lecture.